All right, hello everyone. Welcome to the next lecture, second part of the lecture number two. In this lecture, we will continue to talk about natural response of an RL circuit. We are going to do one example problem, and then we are going to very quickly drive in expressions for the voltage, energy, and power in the RL circuit in case of a natural response. And we are going to have a kind of a quick discussion on a time constant. Very interesting parameter, by the way. So we're gonna have a quick discussion on that. So this is where we stop, and I told you that you can use the stepwise processes for solving some of the example problems. Please remember that, right? So this was a natural response of an RL circuit equation for the current, which is I naught e raised to power t over tau, and the step number one is practically finding the value of the I naught uh, by analyzing the circuit before the switching event, t is less than 0, finding the value of the tau after the switching event, and then substituting both the values of the tau and I naught into this equation, and then solving the rest of the circuit. Practically, you need to solve this equation for this one. Okay, so let's get started and solve one of the example problems. Okay, so here is a circuit that is given in one of the book chapter problems. As you can see, this is an RL circuit, right? So you have an inductor over here, and then of course there's a bunch of resistors. And this was the excitation source that was present, a DC current source that was present before the switching event. So this before the switching event, this current source, when connected to an inductor, energized the inductor, if you will, or provided energy to the inductor. So at time t equals to 0, when the switch will be open, this source will be kicked out. And the question is asking us to solve for all of these. Okay, so let's get started. In A, what we want to do is, in A, we have to find the value of the inductor current IL of t for t is greater or equals to 0, or after the switching event has happened. Okay, in order to do that, let's do all the steps, right? And if you remember, step number one was that we needed to find I naught for t is less than 0, right? So let's see how the circuit looks like when we have t is less than 0. So again, remember, before the switching event, your excitation source was connected. And before the switching event steady state was reached, as we discussed in the past, right, which means that some time has passed, the current was stabilized of 20 amperes, and it provided all the energy to the inductor in the magnetic field. So this means that the inductor became a short circuit, right? And that is why you can literally replace an inductor with a short circuit over here. So this is an equivalent circuit at time t equals less than 0. So this practically means that, right, so the switch is closed for a long time, right, and the previous steady state was reached, right? Again, we are analyzing this for t is less than 0. So we know that this means that inductor voltage is 0. And again, as we remember from the past lecture, why the inductor voltage was 0? Because the current became constant. There is no change in the magnetic field, so no induced voltage. So we will have a inductor becomes a short circuit. Inductor becomes short circuit. Okay, so if the inductor becomes short circuit, as we can see, right, your if the inductor is a short circuit, then all the other resistors can potentially be ignored, and I naught would become equals to exactly 20 amperes, right? So your I naught will becomes equals to 20 amperes. Okay. Okay, so this is good. Now let's do step number two. We know that for step number two, what we need to do is we need to find time constant, right? Find time constant. Okay, so let's find time constant, tau, and we know that tau is equals to L over R. Let's find this thing. And we know that we can find this time constant, which represents the amount or the rate of the decay of the current. This needs to be found for t is greater or equal to 0. So first let's draw the circuit, what the circuit is going to look like for t is greater or equal to 0 or after the switching event. After the switching event, we can kind of ignore the excitation source over here, and our circuit will reduce to a very simple circuit, practically just a few resistances and an inductor. A 2 Henry inductor, inductor current in flowing like this, 2 ohms resistor, 10 ohms resistor, and a 40 ohms resistor, plus minus V naught, and the current I naught flowing over here. So this is how the circuit looks like at t is greater or equal to 0. So as we discussed in the past, we can easily find the value of the tau. So since we have multiple resistors, so the equation for the tau is going to become one inductor and the equivalent resistance of the resistors. So we already know that inductor is, let's find first our equivalent resistance of the equivalent. We have three resistances, right? Just by looking at it, I know that 40 ohms is in parallel with 10 ohms, and this parallel resistance 10 and 40 is in series with 2 ohms, right? So I can easily do 2 plus 10 ohms in parallel with 40 ohms. So practically 2 plus 400 divided by 50 comes out to be 8. So our equivalent is 10 ohms. Okay, cool. So I can replace that over here. So my tau becomes L, which is 2 divided by 10.5. Nice. Sorry, 2 divided by 10 is 0.2 ohms. 0.2 seconds, huh? 0.2 seconds, not 0.5. Yeah, it should be, yeah. 5 over 10 should be 0.5. Okay, so 2 over 10 is 0.2 seconds. So we got the value of the tau and we got the value of the I naught. We can replace those values and we can move to performing the step number 3, which is essentially replacing these values in the inductor current equation that we derived previously. Okay, so step number 3. In step 3, we need to write down the equation for the inductor current. So IL of t, we know that equals to I naught e raised to power minus t over tau. So this comes out to be 20 e raised to power minus t over tau, which is 0.2. And of course, you can rewrite this as IL over t, 20 times e raised to power minus. So 1 over 0.2 equals 5t amperes. And again, this is at t is greater or equals to 0. So here's the equation of the inductor current that the problem asks you to solve. Okay, now let's do the second part of the problem, which is finding the value of I naught. Okay. So B, find the value of I naught of t. Okay, so for t is greater or equals to 0 positive. Okay, again, the circuit is represented over here for t is greater or equals to 0, right? And I can maybe redraw the circuit very quickly if this helps. Right, so this is 10 ohms, this is 40 ohms, 2 ohms and 2 Henry. This is inductor current, I naught, and plus minus V. Okay, so again, this is a circuit for t is greater or equal to 0. Okay, so I need to find the value of the I naught of t. So I naught of t can be, I can, right, so I naught of t is flowing through 40 ohms of resistor over here. I can easily do this thing by using a current divider rule that we discussed in the past lectures. And again, I naught can be easily represented by IL, which is like IL times the other resistance, which is 10 over here, divided by the sum of the two resistances, 10 plus 40. 10 plus 40, right? And again, 10 over 10 plus 40 is I naught equals IL. 10 over 10 plus 40, 10 over 50 comes out to be zero point 0.2 times IL of t. And again, I naught of t equals 0.2 times, so I'm going to replace this over here. 0.2 times 20 is 4. Okay, sorry, one more thing that I kind of missed. The direction of the current over here was downward, right? IL. And in the case of, if you remember, in a current divider rule derivation, our assumption of the direction of the current was upward, is in the opposite direction. So if you were to apply the current divider rule exactly as is without redriving the whole thing, practically you have to use a negative sign over here. Okay, so minus 0.2 times IL, which is 20 e raised to power minus t over tau, which is 0.2. You will be left with minus 0.2 times 20 minus 4 e raised to power minus 5t amperes, right? This is this. So this is the value of the I naught that you would get. One important point over here, why they are asking you to find the value of, right? So why it was asked to find the value of I naught for t is greater and equal to 0 positive, and not t is greater or equals to 0, right? I naught IL of t was for t is greater or equals to 0, but I naught is only for the 0 positive. And the reason for that is, again, exactly at time 0, right, the circuit was, there is no instantaneous change in the inductor current, right? So the amount of the current that was flowing exactly at time 0 and 0 minus was in through the resistor was exactly 0, because there was a short circuit there in the inductor. Okay, great. So we did that. We have a value of the I naught. Let's find out what do we need to do for the C. C is, let's find the value of the V naught. V naught of t. Okay, so let's solve for C. C is V naught of t for t is greater or equal to 0 positive. Again, V naught, this V naught of t is also across the resistor, 40 ohms resistor. So again, this voltage will only appear, or the I naught is only flowing at 0 positive and not before that. That is why we are finding V naught for 0 positive and not 0 negative or even at 0. Okay, so V naught is simple by using an Ohm's law. So V naught of t equals I times R, I naught of t times R. I naught of t is, or what is R? R is 40 times I naught. I naught is minus 4 e raised to power minus 5t amperes. So V naught of t comes out to be equals to minus 160 e raised to power minus 5t amperes. Okay. So this is the value of the V naught of t. Okay. The final thing would be, we want to find this thing. The D part is, it asks you to find the percentage of the total energy stored in the inductor that is dissipated in the 10 ohms resistor. Please understand this thing, right? It is asking you to find how much of the energy that was originally stored in the inductor due to the excitation source, which was removed at the switching event, has been dissipated in the 10 ohms resistor. After the switching event, the energy that was stored in the inductor will be dissipated in all the resistors, right? But it is asking you to only figure out how much of that was dissipated in the 10 ohms resistor in this one. So first we are going to find, right? So essentially we have to do two things. We have to find the original energy, total energy that was stored in the inductor, and then we have to find the energy that was dissipated in the 10 ohms resistor and find that percentage out. Okay. So let's start with finding how much was the power that was dissipated in a 10 ohm resistor. Power dissipated in 10 ohms resistor, right? So you can easily find the power dissipated in a 10 ohms resistor. Again, you can use any of the formula, vi I squared r, or v naught v squared over r. So v naught squared over r is, you already know this value, right? So again, if I were to take a square of this, 160 square should come out to be 2560, and negative should become positive, and e raised to power minus 5t square should come out to be e raised to power minus 10t watts. And of course, yeah, this, there should be another 0, and the resistor is 10 ohms, so this 10 should be divided like this: 2560 e raised to power minus 10t watts. This is the amount of the power that was dissipated. Again, this is the amount of the power that was dissipated in the 10 ohms resistor. Now let's figure it out, how much was the energy initially stored in the inductor, right? Okay. Energy initially stored in 2 Henry inductor. And you can easily figure it out, because we kind of derived this equation in the last lecture, in one of the original introduction lectures, where we looked at how much was the energy that is stored in an inductor, right? Where W was equals to half Li square. Half Li square. Right? So this again is half L I. I is your inductor current. And what was the total amount of the inductor current when the steady state was reached can be represented here like this, right? So half times L, 2 Henry, IL naught is the original current I naught at t is less than 0 in step number 1 of the part A problem, which was 20 amperes. So 20, and I'm going to take a square of this 20, right? So this energy comes out to be approximately, not approximately, exactly equals to 400 joules. Okay, so we find it the total power that was dissipated in a 10 ohm resistor. Then we found the total energy that was dissipated, that was stored in the inductor. Now we are going to find the energy dissipated in 10 ohms resistor. Energy dissipated in 10 ohms resistor. Okay, now let's figure it out, how much energy was consumed by the resistor, right? And we're gonna do a more detailed derivation, but if you remember, again, the solution, again, the simple derivation in one of the introduction lectures, again, energy is a product of the power and the time, and we did that where we said that the power is dw by dt, right? From that you can easily get this equation where the energy dissipated in a 10 ohms resistor should be equals to over time, right? So we want, since we are doing t is greater or equals to 0 positive to all the way to infinity, so the total amount of the energy that was dissipated, let's call it total, over time. And eventually the inductor current is going to go down, right? From e raised to power minus decay exponent values. Okay, so we get 0 power t, and we get power equation is 2, so essentially it comes out to be p10 dt, so 0 to infinity, 2560 e raised to power minus 10t, and this is going to come out to be 256 joules. So one more thing, how this comes out to be 256 joules, because 0 to infinity e raised to power minus 10 t dt is equal to 1 over 10. And why this equals to 1 over 10, I did a whole derivation that is available in the next slide. I'm going to show you in a second. Okay, but anyhow, in this, while solving this problem, first we found the power dissipated in a 10 ohms resistor, then we find the initial energy that is stored in the inductor, right? Before the switching event happened, that was the total energy that was stored. And now that energy needs to be dissipated in this natural response, right? In all the resistors, but we are only interested in the 10 ohms resistor. So we find the total energy that got lost in the 10 ohms resistor, which is 256 joules, right? So percentage of the energy that was lost, percentage energy lost in 10 ohms resistor comes out to be 256 divided by 400 times 100, comes out approximately 64%. So 64% of the energy got dissipated in a 10 ohms resistor and the rest of it in the other resistors. Again, you needed to find the overall energy that was initially stored and how much energy was lost in a 10 ohms resistor to solve this problem. And this derivation is essentially on this slide, right? So you start from here and you ended up deriving this part, that 0 to infinity e raised to power minus 10t equals to 1 over 10. Okay, now let's do a couple of other derivations before we move on to kind of finish this RL natural response part of the whole thing. We already did this a little bit in the example problem, but I want to kind of officially do it and provide you more formal equations as well. Again, this is your RL circuit, a natural response, t equals to 0, removing the excitation source. So we are only left with this. And again, this is your circuit at t is greater or equals to 0 after the switching event will happen. And we already know the value of the current as we derived last time, which is equals to I naught e raised to power minus t over tau. Okay. So let's start. We want to find the expressions for the voltage, power, and energy. So let's start with finding the expression for the voltage. Again, we can easily find the value of this voltage, V of t, by using Ohm's law, right? I times R, I of t times R. So let's find the expression for the voltage. V of t, this V of t should be equals to I of t times R. And again, I is equals I naught times R, e raised to power minus t over tau, right? And this should be right. And again, this is for t is greater or equals to 0 positive. Again, I have defined, I want to make this point again while talking about this. My original I of t, right? My original I of t was I naught e raised to power minus t over tau, and that was for t is greater or equals to 0. So why over here I am saying this should be equals to 0 positive? I am making this point again. I explained that in the example problem, right? So the point is that the voltage across the resistor exactly at time 0 was 0. And why is that? Because the amount of the value of the inductor current I, right, through the resistor does not change instantaneously. So the problem was that, again, as we discussed in the past, right, the inductor becomes a short circuit when it reaches a steady state. So when it reaches a steady state, inductor is a short circuit, so no current is flowing through your resistor. So as soon as you are going to turn off the switch, kick the excitation source out, at that very instant, still nothing is happening to the voltage across the resistor, right? Because all the current is still going through the inductor. However, exactly at time 0 positive, there then the current will start to be established and the voltage will start to establish as well. So that is why, other than the inductor itself, right, rest of the dissipative elements, which in this case is a resistor, only makes sense, or these expressions make sense at t0 positive rather than exactly at 0, right? So this is what I exactly said, that the value of the voltage at 0 negative was exactly equals to 0 volts. The value of the voltage V at 0 positive was equals to I naught R, right? And again, why it was I naught R? Because it was exactly at that instant, right? And then of course, after, as we move away from 0 positive on the time axis, right, you're gonna have an exponent, and that exponent is going to decay the value of the voltage as well. Okay, so this is good. We ended up finding the value of the voltage, expression for the voltage. Let's find the expression for the power. And expression of the power is always easy, right? So we already know that power equals VI, power equals V squared over R, power equals I square R. So these are kind of the general power expressions, right? So we can use any of these power expression over here. So for example, if I were to pick one, this one, and we have picked like two or three of them in the previous derivations in the recap lecture, right? So okay, so power equals I squared R. So I can easily take a square of this, which is gonna come out to be I naught square, right? Times R, so that I can have an exponent at the right hand side. E raised to power minus 2 times t over tau, right? Because of the square thing. And again, this power dissipated in the resistor only makes sense at 0 positive. This is a power dissipated in resistor. Power dissipated in resistor. Okay. Now let's do energy dissipated in resistor, or energy delivered to resistor. Okay. So how we can find energy delivered to the resistor? Again, as you remember, in the initial introduction lecture where we were doing a recap, we said that our power equals dW by dt. Sorry. Okay. Maybe we can do this calculation on the next slide. Slightly. Not that long of a derivation, but still we can do the over there. Okay. So energy delivered to resistor. From the introduction lecture, you should know that we did this thing where energy was represented by the letter W. So power was the rate of change of energy that we did last time, right? So dW should be equals to P times dt. Then we said that we're going to take an integral on both sides, right? So if I were to take an integral over here, so 0 to W for the energy, and then I'm going to change or replace the variable of integration with another variable. I'm just going to say it as an x, so it is going to come out to be dx. And then over here, my limits of integration would be with respect to time, so 0 to t, all the way over there, p times, and again, this is t. I'm going to replace this variable as well, and I'm going to call it, for example, x or y. Let's call this y and this x. It doesn't matter. We could have done other way as well, but I want to put the expression for the p over here too, right? So 0 to t, and expression of the p is coming from here. This one, I naught squared r e raised to 1 minus 2 t over tau. Right? So it should come out to be I naught squared r e raised to power minus 2. Again, there was a variable t, which has now been replaced by x divided by tau. Right? And again, a variable of integration is dx. Again, this thing will become w minus 0 equals 0 to t I naught squared r e raised to power minus 2x over tau dx. W is equals to, let's take out I naught squared r out, 0 to t e raised to power minus 2 times x over tau dx, right? Okay. I want to solve this a little bit more with an identity. And this is, again, you can, maybe I can quickly show you, right? So for example, sorry, okay. For example, if you were to integrate e raised to power kx from 0 to t with respect to dx, right, you're going to get 1 over k e raised to power kx 0 to t. So this is how you actually do this integration, right? And then this is going to come out to be 1 over k e raised to power kt minus e raised to power 0. This is going to come out to be 1 over k e raised to power kt minus 1, right? So if you will do this integration 0 to t e raised to power minus kx over dx, this is what you get. So I'm going to use essentially this thing now and apply this thing over here. So your work done comes out to be I naught square r, I naught square times r, and again you have the same limits of integration 0 to t and minus 2x over t, right? So essentially I naught square over r, and then you're gonna get tau over 2, and then you're gonna get 1 minus e raised to power minus 2t over tau. Again, important thing is that why this looks a little different, because you have kind of replaced the negative sign. This thing should have come out to be minus tau over 2. So we kind of multiplied the minus in the inside parentheses. Okay, so I can replace tau equals L over R. Again, I naught square R L over R times 2, 1 minus e raised to power minus 2t over tau. R are cancelled. So you get W equals to I naught square L over 2, 1 minus e raised to power minus 2t over tau. So this is a expression for the energy, and again this is the energy that is delivered to the resistor, and it only makes sense for t is equal to 0 positive. Okay, so this is the end of this derivation as well. The point is we spent a lot of time in this lecture doing this derivation, and I'm going to spend less time going into those basics more and more. Still continue doing that, but over the progression of this course we'll start to reduce talking about it multiple times. Okay, so the most important thing over here, remember the difference in between 0 positive and 0. The value of the inductor current makes sense at t is exactly equals to 0 and greater than 0, but the value of the voltage or the current or the energy dissipation or the power through a resistive element, a resistor, will not make sense exactly at 0 because it was a short circuit before the switching event, right, at 0 minus. And we just did the switching event at 0, and the conductor current cannot change instantaneously exactly at that instant. So that is why everything is valid for the resistor at t is equal to 0 positive, and for the inductor itself, the inductor current is valid for exactly at equals to greater or equal to 0 as well. Okay, so this is good, right? We are going to do less derivations. Again, I'm doing a lot of this derivation. By the way, one of these derivations can potentially come in exam as well. I do want you to pay attention to these derivations, right? So the idea is that you would be able, if you were to just pick the end expressions, you can potentially solve the example problems and the chapter problems, right? But this will not give you enough thought that if you were to come up with a very innovative new kind of a thing, that you would be able to solve the circuit itself. Okay, moving on. Some very interesting comments on the discussion on the time constant. Very important, beautiful thing, time constant, right? So we ended up defining this kind of a time constant, and we already alluded that in this expression of the inductor current, I naught e raised to 1 minus t over tau, we said that, again, this is valid for t equals to 0, right? We said that, okay, it's at the switching event, my current is equals to I naught. But then as the time will progress, it will start to decay at the rate of tau. So this is the very important thing. So again, time constant is an important parameter for the first order circuit, and essentially as the time, so the way that we kind of report is, we reported that what is going to be the value of the current after 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. And for example, just to give an example, if you were to replace this equation, e raised to power minus t over tau, and replace t equals to 1 tau, right, you will figure out that e raised to power, again, it is going to become e raised to power minus 1, right? So you're going to see that it is going to come out to be 37% percent of the initial value, right? So the current is going to come out to be approximately, right, 37% of I naught. So at 1 tau, your current becomes 37% of I naught. At approximately 5 tau, you have already to a certain level reached the final value because you are 1% of your original I naught current, right? You have already lost more than 99% of the current and you are just left over with less than 1%. So this is the significance of 5 tau. 5 tau is usually in this energy dissipating and the charging circuit means in this case natural response energy is dissipating, right? Means that 19 more than 99% of the energy is already been dissipated after 5 tau. That is why the kind of this tau thing is so important, right? So your current and the voltages values have already reached, have essentially reached by, right? It's not exactly reached because you still have an exponent going down, but practically you have reached those final steady state values. So essentially, once you perform that switching event, remove the excitation source, within this a few taus, you are getting this transient response, but then it is moving on to the steady state response. Okay, approximately a 5 taus. One last thing about time constant, and again, this is another beautiful thing about a time constant. Let's look at this plot. We already know this is current in a natural response of an RL circuit with respect to time, and this blue curve is this our equation that we have looked by now multiple times, I naught e raised to the power minus t over tau, which shows that at exactly time equals to 0, the value of the current was exactly equals to I naught. And then as we move away from 0, positive, after the switching event, your current starts to decay and can be represented by this equation. Okay, great. So this is the natural response of our typical RL circuit decay curve looks like. The interesting thing is that, let's do one more kind of a hypothetical exercise here. I want you to figure it out, right? What is the amount of the drop in current exactly at t0 equals t positive, right? The value of the current at 0 was equals to I naught, right? Because you can easily put like over here, if you will put t equals to 0, I of t becomes I naught. Okay. Anyhow, at t equals to 0, positive current is going to start to decay, right? And we are interested in what is that amount of decay. Okay. So let's see how we can find it out. Essentially, what we need to do, we just need to take a derivative with respect to time over here on both sides. So, right, so we can do it over here, di by dt, and we can take a derivative over here as well. Right, so for example, I can take di of t by dt equals I naught is a constant, d over dt e raised to the power minus t over tau. I naught, right, e raised to the power minus t over tau is minus 1 over tau, e raised to the power minus t over tau. So this is how it comes out to be this, right? Minus I naught over tau, e raised to the power minus t over tau. So this is the change in the current, right? Exactly at 0 positive. Now, interestingly, let's see what would happen. So this again, this equation represents a change in the current. So let's see what will happen exactly at t equals 0 positive. So right after the switching event, e raised to power 0 positive means that you can potentially pick 0.0001 seconds, right? Rather than t equals to 0, t equals to 0 means I of t equals I naught. However, t equals to 0.00000 means that your E naught will become approximately equals to 1, right? Again. And you can potentially place this thing over here. And if you were to place this thing over here, right? So di by dt at 0 positive is going to come out to be minus I naught over t. So this is the amount of the decay that will start to happen, right? And as we know from maths, that the slope of a line is essentially the derivative of that function, right? So derivative of a function is practically slope of a function. So what we are essentially doing over here is, what does this represent? So this practically represents slope of I of t at time 0 positive, right? So this is where the black line is coming from. Right at 0 positive, right after time t equals to 0, we can draw a tangent line, and this tangent line is our black line that is intersecting time axis at tau. We are gonna come to this point in a second, right? But essentially, by now we figured it out that if we were to take a rate of change of current, uh, um, this will come out to be minus I naught over t, e raised to power minus or t over tau, and at t is equal to 0 positive, which is almost 0, comes out to be minus I naught over tau. Okay, so the initial slope of the current curve is minus I naught over tau. So can we find the equation for the straight line, a linear line, this kind of a black line over here? This, again, this is a linear curve, and we can represent the linear curve by y equals mx plus c plus mx, right? So in this equation, our y is I, our x is t, our exponent, right? So c, what is c over here? Our exponent c is I naught, and our slope, m is the slope, is minus I naught over tau. So we can replace all of that over here to come up with a linear equation. And this is our linear equation, right? So we got a linear equation of I naught, which is equals to the intercept, minus I naught over tau, which is a slope, and t is your x-axis variable over here, right? So this is a linear equation represented over here. So this is great. We ended up finding the equation for this black curve as well. The point and the useful thing is coming up shortly. Just a second. So what we are interested in, we want to find out at what point in time on the time axis it will intersect, right? So essentially, I am interested in finding this time at which I will become equals to 0, the value of the t, right? And we can easily do that by replacing I over equals to 0 over here, right? So if we replace I equals to 0 over here, we get I naught minus I naught over tau times t, right? So I naught goes over here. So we get I naught over tau t equals I naught cancelled. So t becomes equals to tau. So this is how we figured it out that it should intersect the x-axis at tau. Important thing. The dark bluish curve in this plot represents the real thing. Your real current decays exponentially with e raised to power minus t over tau and the initial current I naught. The black curves represents a hypothetical scenario where if your decay in the current will not decrease by an exponent factor, but your decay in the current is continue to decrease by this factor, by the slope amount minus I naught over tau amount, right? Your current is going to decrease at an exponential, but exactly right after switching event, it will start to decrease by this factor, minus I naught over tau. And if this would have continued to decrease by this factor, you would have gotten a 0 amount of the current in one time constant. But since it was decreasing by an exponent, e raised to power minus t over tau, that is why you get to approximately the final value in 5 tau. Okay, so this is a much more realistic in a true exponential decay, that after 1 tau, you get approximately 37% of I naught. In a hypothetical scenario, if your current decay were to happen at the same rate at which it decayed at 0 positive, minus I naught over tau, then you would have decayed your entire current and I would have become 0 at 1 tau, which is a hypothetical scenario. Why this hypothetical scenario is important? Because of this tau. Why we ended up doing this exercise is, in a situation where I gave you a circuit and I would ask you that I do not have a value of the resistance and the inductance, and I would ask you in the lab to find me a value of the tau. How in the world you're going to do that, right? The way to do would be you can use an oscilloscope and you can plot this IL curve. Once you will plot this IL curve, you can potentially draw a tangent right at the start of the curve. And the point is that the point at which it will intersect the x-axis over here would be the very good approximation of the tau value, right? So in case if we don't know the R and L values in the circuit, we can find the natural response current on the oscilloscope of the RL circuit and then use a tangent line to intersect the x-axis and reasonably determine the time constant indirectly. So this is how we can indirectly determine the time constant as well to using a graphical method. This is why this time constant is very important. Okay, so this is pretty much it of this lecture. So a couple of take-home messages. We spend more time than needed in terms of the derivation and figuring out what to do in an RL circuit. We're going to be slightly more quicker in the upcoming lectures on the rest of the natural response of an RC circuit and the step responses of the RL and RC circuit. We're going to be slightly more quicker than this. But the point that I'm trying to make is please pay attention to all the derivations. We're going to do derivations much more quicker. If there's any supplementary derivations that are needed, I can just provide you those supplementary as a supplementary slide like I did over here as well in one of the slides here. We're going to continue doing the example problems. Time constant is very beautiful thing, right? Because time constant represents the natural decay of the current, and we're going to see how it will decay the voltages as well in the capacitor case. And we can realize that at one time constant our values will become 37% of the original values, and at 5 time constant it will become approximately only 1% of the less than 1% of the original values. So time constant are very important because they give you a real estimate of how soon you can achieve your steady state, how soon your circuit becomes stable. Okay, cool. So this is it. I'm going to talk to you in the next lecture. Thank you. Bye bye.